Hello, I'm Shima Khalaf, and this video is about linear regression and correlation. First, I will talk about them a little, then I will give an example of them. I already wrote this down because it was hard for me to talk and write at the same time, and it would take a lot of time. So, as we know, correlation is a linear relationship between two variables. Simply said, it means they change together at a constant rate. Each variable represents a particular problem. If one of the two problems changes in a certain direction, the second one changes in the same direction or the opposite direction of the first one. And the change of the two problems at the same direction, meaning if the first one increases, the second one increases too. And if the first one decreases, the second one decreases too. It means the relationship is increasing or positive. The correlation, sorry. But if the first one increases but the second one decreases, or vice versa, the first one and the second one decreases, or the first one decreases and the second one increases, it means the correlation is reverse or negative. The link is complete between two variables. That means if we know the value of one of them, we know the value of the other completely. Measure link strength between two variables with the correlation coefficient to investigate the effect of one of the two variables on the other. We find the algebraic relationship known as the regression equation, which is a linear relationship between the two variables x and y. As for the regression is one of the methods of data analysis which is used to clarify the relationship between variables, as it enables the researchers to predict the value of one variable, the dependent variable, to the value of the other variable, the independent variables, in order for the value of the dependent variable to be predicted with the knowledge of the independent variable. The relationship between them must be placed in the form of a mathematical equation, and for the regression analysis is used to discover the relationship between the two variables. In this video again, I will consider an example of linear regression and correlation given the following 6 pairs of data. So we have two variables x and y and following pairs. So -1, -1, 1, 2, 2, 3, 4, 3, 6, 5, and 7, 8. Now, these variables could be any variables. We could assume, for example, that x is at any particular time, whether a stock went up or down. Same thing for y. So this pair could be at any particular time. A stock x went down by $1 and a stock y went down by $1. At another particular time, a stock x went up by $1 and stock y went up by $2. So we're following at different points of view in time the trend for two stocks. So we have our 6 pairs, and the question is, does there exist a linear relationship between the two variables? And if there is, how good is it? So of course we will find the linear least squares, and to measure how good of a linear relationship it is, this will be given to us by the coefficient of correlation, and all we need to compute them is to construct a symbol table for the sum of the x squared, y squared, and xy values. So once we have this table, it will be very straightforward to compute both the linear squares, so our linear regression and our coefficient of correlation. So here's the table. First column is for x, your -1, 1, 2, 4, 6, 7. Column 2 for y, -1, and of course the corresponding y values goes -1 bit goes with -1, 2 goes with 1, and so forward. And we need 3 more columns for x squared. It will be 1, 1, 4, 16, 36, and 49. For y squared will be 1, 4, 9, 9, 25, and 64. And the corresponding values are values cross terms. Will be 1, 2, 6, 12, 30, and 56. And then we need the total of these columns. And all we need is a summation of x's, y's, x squared, that's better, y squared, and the summation of xy. And we put the totals at the bottom of our table. And using the sigma notation, adding all this will be 19. Adding y's, it will be 20. X squared will be 107. Y squared will be 112. And xy will be 107. So now that we have our table, we can use it to find our linear squares and our coefficient of correlation. And n is the number of our pairs. We have 6 pairs. So the equation for our linear squares, so y will be given by slope a hat times x plus intercept b hat. First we find the a hat. The formula given as a function of our columns, totals, and the number of data pairs. So it will be the summation of x times summation y minus n times xy over squared minus n squared individually. And we have everything, so we just replace it. 90 times 20 minus 6 times 107, 90 squared minus 6 times 107. And it would be negative 262 over 281 negative, and it will approximately will be 0.9324 with 4 decimal place. So now we have a slope for our line of least squares. Now let's find the second value, y-intercept b hat. The formula is x summation times xy's minus summation of y times x squared over like the same of it as a hat. And again, we have everything and we just replace it. 107 minus 20 times 107 over 90 squared minus 6 times and it will be approximately 0.3808. We round it up to the 4 decimal place, and that is our second value. Now we have the equation of line of least squares. Y is approximately, and these approximate values. So now 4 x plus 0.3808. But again, the idea is once we have line of squares, we would like to possibly use it to make prediction. So if you knew the x values, this could help you predict accurately the corresponding y value. But the answer of our prediction are only accurate as the strength of the linear regression, and that is given of course by coefficient of correlation. So let's compute this. We must first compute two additional quantities, the standard deviation for the sample of x values. We have 6 values and the standard deviation of y values, and then we can solve for coefficient of correlation. And for standard of x values, standard variation for x values, 6. So we take the variance, so we must sum the difference between each x values and the sample mean x values squared, divided by number of values, so n minus 1. That is the sample variance. The standard deviation, of course, is the square root of the variance. And we will span this out and simplify it. This is easier because now we have everything and we just replace it. Will be 107 minus 1619 squared, and this is 5, and this will approximately will be 3.0605. And we round it up to the 4th decimal place. Now we have the standard deviation for the x values, and for y is the same thing. We just replace the x's with y's, of course. And $112 minus and this will be approximately 3.0111. So we have the standard deviation for the x values and the y values, and now we can find our coefficient of correlation and for the y value. And yeah, there are actually two ways of finding r. The first way, which is now going to be shorter because we have previously found the slope of our line of least squares, and the second method, we can find r independently, and r is simply going to be sx over sy times a hat. And the approximate value for this will be 0.9477. Notice that this is really close to 1. So we have a very strong here correlation, which means the points in our scatter plot would be really close to the line of least squares, which says that the prediction that we can make should be pretty accurate. So if we had a very small values of r, and if the r was 0.02, then we would have a weak correlation. And if we had a weak linear relationship between two variables, we couldn't use the equation for line of least squares to make prediction. So the values were -1, -1, 1, 2, 2, 3, 6, 5, 7, 8. So notice that we only get values for x that are always between -1 and 7. For x. And we get values for y that are between -1 and 8. And we found that our line of least squares was approximately 0.9324 times x plus 0.3808. And we also had a very strong correlation, which again is the only reason we can justify using the line of least squares to make prediction about x and y values. R was approximately 9.477, which again is very close to 1. So let's look at one example of what's called interpolation. Suppose that we know the behavior of the first stock at a particular time. Suppose we say that the stock in that time increased by $5. We may ask then, given the information about X, what is the in that particular time, what is the predicted value for Y? So first thing is, as we get data to this particular X value, if you look at our table, nowhere we gathered the data when X was 5. So we don't have it in our table. So we have to go back to our next best option, being the predicting the value from our linear least squares. And it's interpolation because the value X equals 5 is within the range of our observed values between -1 and 7. So we just replace it in the equation. Nine, 3, 2, 4 times X, which is 5, plus and it will approximately will be 5.40 428. And that is the predicted Y value given that the X was observed to be 5 from our linear least squares. Now, what about an extrapolation? Same question, what if we have an observed value for the first stock that is $12? And so what is the predicted Y value? Now we can't use our linear least squares. We can't use our linear least squares for this because we only gathered data between -1 and 7. So all we have right now is evidence of a strong linear relationship between X and Y, as X is between -1 and 7. But there is no guarantee that above 7 and below -1 there will be any relationship. This relationship would still hold. It may break down. It is not because a linear relationship exists between two variables over a certain interval that it does exist forever. So here 12 is out of our side of our range. For X values, the linear relationship could break down, so we cannot make prediction here. Now I do one last example of interpolation, but backwards. This will be again interpolation, but what if now we know of an observed value for the second stock that is going up by 4.5. And we want the predicted X value. Well, once again, we use our linear least squares, as our Y value is 4.5, and it's between our observed range of Y values, so we replace it in our equation. So 4.5 will be approximately 1x 9324 times x plus 0.08, and we can simply solve this. And we do division. And x is approximately 44178, the fourth decimal place. And that was it. Thank you so much for watching.